Welcome back to analog electronics lectures. Today is lecture 29 and we are going to talk about the cascade amplifier. Actually in the last class we had the intention of talking about both cascode and cascade, but clearly I was over ambitious, right. We only managed to do the cascode. Today we will talk about the cascaded amplifier with the effect of capacitances. Now, you would think that the cascaded amplifier is easy, it is not. Okay. So, let us just draw one, and the DC stuff is very easy. So, we will quickly do the DC stuff and then move on to the AC. So, this is the cascade amplifier, right, two common source amplifiers one after the other, and let us call them M1, M2, R1, R2. If you think of each separately, then this has an output impedance of RDS1 in parallel with R1. This has a transconductance of GM1, okay, and therefore, the gain is GM1 minus GM1 times R1 in parallel with RDS1, and the same happens to the second one. Okay. So, it looks very straightforward. The second one will, I mean overall you will have a gain of GM1 times GM2 times R1 in parallel with RDS1 and R2 in parallel with RDS2. You could also do this a little differently. You could just find out the output impedance from the second stage. The output impedance from the second stage is R2 in parallel with RDS2. This is the output impedance, and the transconductance from just the second stage. I will apply V in over here and measure the short circuit current at the output of the second stage, right. If I apply V in over here, that is going to create GM minus GM1 times R1 parallel RDS1 over here, and that will create GM2 times that will be the short circuit current. So, the short circuit current is GM1 GM2 times R1 in parallel with RDS1, and that is it. So, you have got the overall short circuit current, transconductance, this is the overall short circuit transconductance, this is the overall output impedance, the product of the two is the voltage gain. Okay. So, it is same story, it is the same story, I did it in two different ways. This is what happens at DC. So, it is very easy to work out at DC. However, our business is not at DC anymore, right. DC was a long time back, right, 20 lectures back we were thinking of DC. Now, we have to plug in the capacitors, okay, and I have 4 capacitors for each device. So, let us do M1 first. I have got CGS1 and I have got CGD1, and once again you see CGD1 is going to be very annoying, okay, very annoying CGD1, and then I have got C drain to body of 1, I have got C source to body of 1, but that need not be drawn at all because source is at ground, body is also at ground. Okay. So, you need not worry about source to body. Then device number 2, I have got CGS of 2. Now, CGS of 2 and CDB of 1 are in shunt. Okay. Then I have got CGD of 2 which is even more annoying than CGD1. Okay. Think about CGD1 was annoying, CGD2 is even more annoying, because at least in CGD1 sometimes this side is going to be grounded and so on, you have some respite. Here there is no respite. This is the most annoying one of the lot. And then you have C drain to body of 2. And finally, you have C source to body of 2, but that is also irrelevant because both source and body are at ground. Okay. Now, we need to I do not want to keep drawing this again and again. So, I will label the nodes a little bit. So, I am going to call this node number 1. I think last time we did the input was called as node number 1. This I am going to call as node number 2 and this I am going to call as node number 3. And now I am going to redraw it, and you know what these capacitors are, just that I am going to call CGS1 as C1 and I am going to call CGD1 as C12 and I am going to call this CDB1 plus CGS2 as C2, and then instead of CGD2 I am going to call it C23, and lastly I am going to have C3 instead of CDB2. Okay. So, this is the circuit that I am going to analyze, and you know what these C1, C12, C2 what these are, right, they correspond to these values. Okay. So, this is the notation we are going to use right now. What do you want to do? Shall we do the short circuit transconductance first? Let us do that, because I know in advance it happens to be easier. Okay. I know it is easier to work out the short circuit transconductance. Let us do that first. So, when I do the short circuit transconductance over here, the output is grounded. Okay. And we are going to measure the current through this output. So, when I ground this output, there is no current through C3, there is no current through R2, okay. These are all irrelevant. RDS2 is gone. Inside this MOSFET there is only GM2, okay, and that is it. So far so good. What about C1? Do I have to worry about C1? No, because it is forming a private loop with V1 and this current is not going to go through the short circuit at all. So, do not worry about C1. All I have is C12, C2 and C23. Okay. So, redraw. that is all. Okay, I have broken up the transistor, I have broken up the M2 to indicate that RDS2 is gone, okay, it is only GM2. Fine. What you will notice is that C23 is not so irritating in this particular setup, all right. If I know the voltage over here, then the current through C23 is easy to find, it is just SC23 times the voltage over here. Now, what is going to be the voltage over here? I have got V in, let us do a KCL over there and figure out the voltage. Okay. So, let us call this voltage as V, V minus V in times SC12, that is the current this way, plus V by R1 plus V by RDS1 plus V times SC2 GM is a minus, no, plus GM times V in, okay, plus V times SC23, this whole thing is equal to 0. Okay. So, ordinarily I do not like writing these KCL equations, but in this case I have written it, please bear with me. Then you put the V ins on one side and the V's on the other side, there are only 2 V in terms, all right, and the others all form the denominator. This was GM1. Okay. And therefore, I know what is V. V is V in times GM1 minus SC12 divided by this whole denominator, all right, but that is no good. I need my answer. My answer, what is my answer? If this is V, this current is V times SC23, this current is GM2 times V. So, what is the short circuit current? The short circuit current is V times SC23 minus GM2. Okay. So, knowing V is not enough, I need to multiply it by that factor, that is the short circuit current. So, my short circuit current finally is, or rather let me write out the short circuit transconductance is what? So, this is the expression for the short circuit transconductance. What did I do? I did V by V in divided by V I am sorry, I found out V in terms of V in. So, V by V in is GM1 minus SC12 divided by this, that was V by V in, but I wanted V times so much, right, that was the current. Current divided by V in is therefore just V by V in times this extra factor. Okay. So, this is my short circuit transconductance, and unfortunately it is not complete, right, you have to put it in the form, all right. And what is the form? The form is DC term times 1 plus the poles, 1 minus the pole, 1 minus the 0 or whatever, product of zeros, product of poles, right. So, you have to take the DC term common outside, and my DC term was quite straightforward. It was just this GM1 GM2 GM1 GM2 divided by 1 by R1 plus 1 by RDS1. Okay. So, I am almost there in fact, GM1 GM2 okay. So, I have to take these things common outside forcefully, even though things are not really common. So, my short circuit transconductance finally looks like this. Okay. What has happened over here? In my short circuit current, I got two right half plane zeros, one right half plane because of SC12 and GM1. Let us look at the circuit. SC12, C12 and GM1 gave me one right half plane 0. So, try to get a feel for what is going on. If you see, there is an M1, there is a path through M1 GM1 and there is another path through SC12 from V in to V. Okay. This is what is creating the right half plane 0. Again, there is a path from V to the output through GM2, there is a path from V to the output through C23, that is what is creating the 0, the right half plane 0. So, you see there is a second term SC23 by GM2. Okay. So, your right half plane 0 is at the location GM2 by SC23, I am sorry C23. So, if you say what is the value of the right half plane 0, it is at GM2 divided by C23, that is the frequency, GM1 divided by C12, that is the frequency. Okay. If you look back, you open your common source amplifier, you will see exactly the same thing. You open your expression for the Cascade amplifier, you see exactly the same thing, GM1 divided by C12, all right. So, something very interesting is going on over here, right. we seem to be lost in the maths, but we are not. Okay. We are trying to develop the intuition over here that the right half plane 0 that we are getting is related to this transconductance and C12, and there are two such right half plane zeros over here, because there were two paths, two times, once over here, once more over here, two right half plane zeros, one is GM1 by C12, the second is GM2 by C23 plus, okay, right half plane 0. All right. So, that is something that we saw. What else are we seeing? We are seeing that there is a pole. The pole is because of RDS1 R1. So, some parallel impedance, parallel resistance of RDS1 and R1, and a capacitance of C12, C2 and C23. Let us look at the circuit. So, if you look at this particular node, there is only one node in this circuit, only one unknown node is there, all other nodes are known. There is V in, this node is 0 volts, there is only one node which is where the voltage is not known. Okay. So, if you look at that particular node, then what is the impedance that you see? You see R1 in parallel with RDS1, R1 in parallel with RDS1, that is the resistance part of it. If you look at the capacitance part of it, you have got C2 to ground, C23 to ground, and you have got C12 to V in, and the 0 part you have already taken care of, right. So, you can think of this as a ground superposition, think superposition, right. So, you have got C2 to ground, C23 to ground, C12 to ground. So, the effective capacitance is C12 plus C23 plus C2. All right. So, if you look at that one node where the voltage was not known, you inspect that one node where the voltage is not known, what is the effective resistance there? It is R1 in parallel with RDS1, there is no other resistance. What is the effective capacitance there? It is C12 plus C2 plus C23, there is nothing else. So, therefore, you can directly write this whole expression by inspection. This was the DC term which you knew beforehand, and then the remaining part, okay, 1 plus SCR is the pole, 1 plus S, what C? The C is the effective capacitance at that one unknown node. What is the R? R is the effective resistance at that one unknown node. All right. And then you are looking at the right half plane zeros. In the right half plane zeros, by now you probably are getting the hint that it is GM1 by S by C12 is one, and GM2 by C23 is the other, and that is it. And the entire expression can be written just by inspection. Okay. So, the idea is to get to a level where you can start writing things by inspection, that is the agenda. Okay. Now, do not always try to write things by inspection, sometimes you have to think as well. Okay. So, let us now go to the second half of the work. So, this is only half of the work, right. The other half of the work is to find the output impedance. And my expected DC quantity is just this much, R2 in parallel with RDS2. I will have to look in from the output, null the input, look in from the output and find the impedance. So, this is my circuit. I have already nulled the input. I had some capacitors around. I had C12 between node 1 and 2, but that C12 is going to add to C2. And then I had C3 between node 3 and ground, and I had C23 between node 2 and node 3. So, this was my circuit. Okay. So, the only important simplification is that C12 is now sorted out. All right. So, we are going to now find the output impedance looking in from here. What is so hard about this? Is this hard? You look in from the output, you see R2 and C3 and maybe RDS 2, right. What about all of this stuff? Does it matter? What is the voltage here? So, ordinarily at DC that voltage used to be ground, because my input was a ground. Okay. So, this current GM was 0 volts, 0 amperes, GM times the input, right, that was 0 amperes, that was flowing through R1 and RDS1. So, therefore, the voltage over here was equal to 0 volts. Okay. But now that is no longer true. This voltage is now related to the output through this capacitance C23. I am telling you, the C23 is going to cause havoc. If C23 had not been there in this picture, then this voltage would have been 0 volts. Okay, C23, if this capacitance had not been in the picture, all right, the voltage here would have been a clean 0, because the input is 0, that created GM1 times 0. GM1 times 0 is flowing through R1, RDS1 and C12 plus C2, and if a 0 is flowing through a RC combination, then the result is a clean 0. Okay. So, there was nothing to be done. All right. Now, what is happening is that I am applying a voltage from outside for the output impedance. What do? You apply a voltage from outside and see how much current is going inside. So, you have applied a voltage outside. Now, when you apply a voltage outside, C23 couples that voltage to this node somehow. So, this node is no longer at 0. Okay, you have applied a voltage V over here. All right, I agree that this current is 0, but that is not the end of the world. Okay. So, let us simplify. Inside this MOSFET, this current is 0. So, let us not draw this MOSFET at all, and let us write this as okay. So, the MOSFET is gone. Okay. In fact, you could probably even draw it like this. Okay. So, you have got R1 in parallel with RDS1 over here, you have got C12 and C2. So, I have put all of that as one Z. have drawn all of that as a combined Z, okay, lumped everything together as one impedance Z from this node to ground. And then in between here and the output you have got C23, and then over here you are applying a voltage V and trying to measure what is the current I, right. This is what you are doing. Now, when you have applied voltage V, there is going to be voltage division between C23 and this impedance Z, and therefore, you will get some voltage at the gate, it will not be 0 anymore. Alright. So, this is the big deal over here, this is the problem. The problem is this C23, the presence of this C23 has coupled the voltage at the output back to the gate of the second MOSFET M2. Okay. And this is going to create current through M2. So, now GM2 is going to come into life, okay, and start drawing current. Fine. You see the complication? The complication is as follows. So, let us just do this. Let us just do this much. I have a MOSFET Z2 across gate and drain and Z1 between gate and ground. What is the impedance looking in? Think for a moment. Let us say Z1 was not there, open circuit, Z1 let us say is very large. If Z1 is very large, then no current flows through Z2, then the voltage over here and the voltage over here are equal. So, if I apply V over here, I get V over here. Now, if I apply V over here, then the MOSFET responds by pulling Gm times V current. Okay. Had this voltage been V, so I have applied V, I am imagining Z1 is not there, okay, if I for now temporarily, I am just trying to understand what happens. So, if I apply V over here, I get V over here, right, because no current goes through Z2, Z1 is not there, open circuit. Now, if I apply V over here, then the MOSFET responds by pulling Gm times V. Okay. Of course, inside the MOSFET there is also some RDS. Okay. RDS is between the output and ground anyway. So, I have got Gm times V current coming this way and I have got RDS. So, the output impedance is going to be RDS in parallel with 1 by Gm. All right. The output conductance is going to be Gm plus GDS. I have applied V, I am getting Gm times V plus GDS times V. So, the output conductance is Gm plus GDS. The output resistance is 1 by Gm in parallel with RDS. All right, this is what happens when Z1 is not there. Now, let us throw Z1 back into the picture. I apply V, what is the voltage I get over here? I will get a voltage division between Z1 and Z2. So, I get V times Z1 by Z1 plus Z2. Okay. What is the MOSFET going to do? It is going to respond by drawing Gm times this voltage. Okay, and of course, RDS is there in parallel. there is also one more path now for current. Current also flows this way. Okay. The current this way is V divided by Z1 plus Z2. All right. So, the net current that comes in from outside is the sum of these two currents. Fine. So, you get V by Z1 plus Z2 times GM Z1 plus 1. Okay, that is the sum of the two currents coming in. So, if this is I, actually there is one more because of RDS. So, let us add that also. All right. So, if you look at the output resistance, so this is the total current. I is V by RDS plus V by Z1 plus Z2 times so much. So, the total output resistance is V divided by I. Okay. Output conductance is I divided by V. I divided by V, let us just do output conductance because it is easier. Okay. So, this is the output conductance. Output resistance would be 1 by of this. Fine. Now, what is our situation? Our situation has Z1 as a combination of all of this, Z2 as C23. Let us leave out this GDS for now, it is just going to come in parallel later on. Okay. So, I will have R2, I will have C3, I will have RDS2 and then I will have the rest. So, if I just focus on the rest, then it is just that is the output conductance. So, let us not look at the other part. So, it is Z1 plus Z2 divided by 1 plus GM Z1. Okay, and then we will place all of these in parallel. Okay. So, output conductance because of GM, I have got output conductance because of GM and that is so much. All right. In our specific case, Z1 is this complicated quantity, Z2 is 1 by SC23. Look at a situation where Z2 is infinity, just test it out. If Z2 is infinity, this output conductance boils down to 0, that is the MOSFET does not respond if Z2 happens to be open circuit, right, sanity check. This is a sanity check. Sometimes you need to do these sanity checks just to see that you are in the right path. Okay, you plug in Z2 equal to infinity. If I plug it in, then immediately I see I by V is equal to 0, which means that the MOSFET does not respond when I apply voltage at the output. Okay, I have de-embedded RDS completely. So, in our case Z1 actually Z1 is hard, 1 by Z1 is something that I have readily. Okay, this is 1 by Z1. I do not even have Z1, and I have got 1 by Z2. Okay, this is what I have. Maybe you want to represent this in terms of 1 by Z1 and 1 by Z2. So, this output conductance is so let us divide numerator and denominator by Z1 Z2. Okay. And what we are now going to do is, we know the value of 1 by Z1 and we know the value of 1 by Z2. 1 by Z1 is the parallel combination of C12 C2 RDS1 R1, and 1 by Z2 is just SC23. Okay. So, this is my output conductance because of the MOSFET, and you have to add to this the other terms RDS1, R2 and C3. Fine. And what is my Z out? Z out is 1 by this entire monster. Okay. Now, where are we leading to? What are we leading to? Can we look at the poles and zeros of Z out? So, it is going to be 1 divided by this whole thing, and naturally you are going to multiply numerator and denominator by this quantity, right. So, this quantity will come to the numerator. Let us write it out cleanly. You have G1 plus GDS1 plus S times C12 plus C2 plus C23. Okay, this is what will come in the numerator, right. Any comments? No comments? There should be a comment. This and the pole of the short circuit current are the same. Okay, the short circuit current had a pole 1 plus S blah blah, right, C12 plus C2 plus C23 times the parallel combination of RDS1 and R1. Here I have the parallel combination of RDS1 and R1, and I have C12 plus C2 plus C23. Okay, of course, I have to take that thing common out, right. As soon as I take G1 plus GDS1 common, right, I will get exactly the same thing. Okay. I mean, you have to take it common. G1 plus GDS1 has to come outside, and then you get exactly the same thing as the pole of the short circuit current. So, the pole of the short circuit current cancels out completely with the 0 of the output impedance. That is something very interesting. This is exactly what happened in the Cascade amplifier as well. Cascade amplifier, the short circuit current had a pole and a 0, right half plane 0 and pole, right, it had one right half plane 0, one pole. Here we had two right half plane zeros and one pole for the short circuit current. Then in the Cascade amplifier, the output impedance had a 0 and then some second order denominator, right. So, a couple of poles which I said you can't factorize, right. So, we do not know where they are as of now, right. Here also it is the same story. The output impedance has 1 0 and then you are going to, I mean, it is a mess right now, it looks like there is a mess over there, right. You can write it up, you will get something, and trust me, you will not be able to factorize it. Okay. So, you will get two poles in the output impedance, 1 0, and this 0 happens to be exactly the same as that of the pole of the short circuit current. All right. So, what does this mean? This means that to analyze this entire thing, so I am not going to write this, okay, you write it. All right, it is just a waste of time. It's some second order polynomial is going to come, and trust me, you are not going to be able to factorize it, neither am I going to try. All right, so I am not going to write it. I do not plan to write it. Okay. Now, what is the deal over here? The deal is that I apply a voltage at the input, I measure short circuit current. This gives me two zeros. One 0 is GM1 by CGD1, another 0 is GM2 by CGD2. Both of these are right half plane zeros. Keep these two aside. Then I am going to apply voltage here and measure the current going in to this particular node itself to measure the output impedance. But here I am not going to worry about the zeros, I am only going to look at the poles. Okay. So, if I try look, and what am I going to do with node 1 at that time? For the output impedance, node 1 is going to be at ground. So, for the output impedance, CGD, this C12 is going to come in shunt with C2, okay, for the output impedance. So, I have one capacitor over here R1 and GM1 is 0, right, GM1 VGS1 is 0. So, over here all I have is R1 in shunt with R1 parallel RDS1 in shunt with C2 and C12, okay, that is the first stage. I keep that first stage and I am applying voltage at the output and trying to figure out what is the current coming in. So, here I am not going to look at the 0, this node is an unknown voltage, right. So, there is going to be a pole because of this node, or 2 poles because of this node, alright. And then I have got R2 and C3, they are going to contribute a pole, right. So, the resistance at this node and the capacitance at this node, they are going to contribute a pole. I do not know what that capacitance, what that resistance is. Resistance is clearly there is some resistance and some capacitance, it is going to contribute a pole. And then the resistance and capacitance at the first node, at node number 2, they are also going to contribute a pole, okay, 2 poles in the system, fine. Now, we are going to take a little detour, and is this understanding okay so far, right. So, any complicated circuit can be broken up, right. You are normally not going to get cascade of 3 amplifiers, okay, it is not going to come, right, that scenario is not going to show up. There is a reason why, we are going to discuss that. There is also this, that more or less if you understand so far, then using the Norton equivalent method you can solve accurately any circuit, okay. All you have to do is apply Norton correctly and you can solve it. I mean, there is going to be some algebra, and sometimes the algebra is going to be so messy that it might look very dirty, right, but you just go through it and work out whatever is required, all right. Now, we are going to take a detour, a slight detour, actually 2 detours. Detour number 1, so the first detour we will just do very quickly right now, and the next detour we will take in the next class. So, the first detour is like this. You see this setup where I have got C23 in shunt is very annoying, okay. So, I am going to just try to simplify a little bit. So, suppose I have got an amplifier of gain equal to minus A, voltage gain, which means if the voltage over here is V, then the voltage over here is going to be minus A times V. If I have a capacitor C over here and I plan to measure the input impedance, then I have got V over here. How do I measure input impedance? I apply a voltage, measure the current. I apply V over here, automatically I get minus AV here. What is the current that the capacitor takes? It has V on one side, minus AV on the other side, right. So, the potential difference is V plus AV, or in other words 1 plus A times V times SC. So, the current taken by the capacitor is 1 plus A times V times SC, okay. Or in other words, the input impedance, I applied V, I got a current of so much. The input admittance is 1 plus A times SC, that is the input admittance. All right. What this means is that the effective capacitance with respect to ground is 1 plus A times C. So, I applied a voltage V over here and I got a current 1 plus A times SC times V through the capacitor, as if it was going to ground. So, this could be a model. Okay. Likewise, if you apply V at the output, okay, then obviously the input has got to be minus V divided by A, because this is an amplifier of minus A, okay, which means that now the potential difference is V times 1 plus 1 by A, and that means that the current that goes this way is 1 plus 1 by A times V times SC. And that means that you could simplify a circuit that looks like this and redraw it in this fashion. Okay. So, this is called Miller's theorem. It is not really, it should not get the status of a theorem according to me, because there are a lot of fallacies in this. I mean, these two circuits are not really equivalent at all, right. In this circuit there was a path from the input to the output, in this circuit there is no path from the input to the output, they just can't be equivalent, right. So, although it is called in the books, it is called Miller's theorem, I ask you to take it with a pinch of salt, it is not a theorem, right. It is some sort of an approximation. So, this approximation can be made to simplify a lot of circuits and give you insight as to what is going on over there, right. It only can be used as a tool to gain insight, all right. If you want to do precise mathematics, then Miller is not for you. So, this is called Miller's theorem, although it should not get the status of theorem, as I said. Okay. So, this can be used to simplify our C23 and C12 and all of those tricky capacitors, right. So, we are going to use this as a tool, we will do it later on. Before that, I am going to take yet another detour, right. This was detour number 1. Okay. So, we discussed the cascaded amplifier today, right. We actually did the complete analysis, right. I am actually quite happy with the analysis. We also discussed Miller's theorem. We will come back to Miller's theorem and the cascade analysis again, right, after the next class. Okay. Thank you.